In this video, we're going to take our model from last time. So this is a queue where people arrive, but they never leave. It's a little kind of Hotel California, if you know the song. Um, so we're going to add in the possibility that people are actually served, in which case they leave the queue. So if you remember, our single person model for a queue where they were being served, right? So inline, and then we had probability mu delta t that they moved to being done, and probability 1 minus mu delta t that they stayed in line. And so if we implement this into our broader queue model where people are arriving, if you think about it, what's going to happen when somebody is done being served? Well, they leave the line, which means the number of people in the line goes down by 1. Okay? And so what we're going to need to do is we're going to put in arrows that represent people leaving the line, which is to say, if somebody leaves the line, the number of people drops from 1 to 0, or it drops from 2 to 1, or from 3 to 2. Okay? Now notice we're making the assumption that only one person leaves the line at a time, that each person is being served one at a time, which if you think about it, like if you're in a supermarket checkout or something like that, this is really the line. If you have more complicated lines where multiple people are being served at a time, you get a more complicated model. Okay? But mu delta t is the probability that somebody leaves the line, so we're going to put that in here. But notice now that we're in a situation where some of these violate our Markov chain condition. Okay? So if you sum up the arrows going out of 0, it's still 1. Lambda delta t plus 1 minus lambda delta t adds up to 1. But the arrows going out of this state, mu delta t, 1 minus lambda delta t, don't quite add up. So we also need to subtract mu delta t from each of these terms. Okay, so 1 minus lambda delta t minus mu delta t, 1 minus lambda delta t minus mu delta t, 1 minus lambda delta t minus mu delta t. Okay? And so you can use this to set up a system of equations, and from that get a system of differential equations, right? So you can say, for example, P0 of t plus delta t is going to equal 1 minus lambda delta t times P0 of t. P1, or say any Pn for a higher n of t plus delta t is 1 minus lambda delta t times Pn of t plus, no, that's right. But that's not the order I wanted to write these in. So lambda delta t times the previous state, right? P sub n minus 1 of t, right? Because you're getting lambda delta t from the previous one, plus the ones that stay in that state, 1 minus lambda delta t times Pn of t, plus the ones that came from the state above, right? When somebody left the line, which is going to be plus mu delta t Pn plus 1 of t. Okay? So for P0, we get this equation. For Pn, we get this one. We can take those and solve for differential equations, kind of like what we did before. So taking those kind of discrete equations, taking the limit as delta t goes to 0, we can get P0 prime of t equals, just like before, negative, I left a term off here. Coming from 1, we have mu delta t P1 of t for P0, right? Because we've also got, if somebody's in the line and they leave, we go back to 0. So P0 prime of t is going to be negative lambda P0 of t plus mu P1 of t, and Pn prime of t is going to be equal to negative lambda plus mu Pn of t plus lambda Pn minus 1 of t plus mu Pn plus 1 of t. Okay? And you get those differential equations just by manipulating things and taking the limit as delta t goes to 0. Now, solving these differential equations, it can be done. It gets you something called the Bessel function. And they're very, very complicated. So we're not actually going to solve them. I am going to give you two facts that come from this model. So these can be computed in much the same way using expected values. You can get that the average wait time of somebody standing in this queue is going to be 1 over mu minus lambda. And if you want to see how that's derived, you can see it in the textbook. So the average time that somebody waits is 1 over mu minus lambda. And then the average queue size, so the average number of people in line, is going to be lambda times that. So lambda over mu minus lambda. Okay, so 1 over mu minus lambda is the average amount of time somebody waits. Lambda over mu minus lambda is the average size of the queue. Okay, so what we're going to do in the next video is I'm going to show you a simulation of this in Excel, just kind of walk you through how I did it, and then talk about kind of seeing these values come out of that.